On July 24th, 2001, a graduate student named Duncan Lorimer was reviewing archive data from the Parkes Observatory in Australia. He was looking through radio telescope observations recorded 6 years earlier. Routine work, the astronomical equivalent of sorting through old files. Then he saw it. A spike in the data so powerful it initially looked like an error. A burst of radio waves lasting less than 5 milliseconds that had traveled across 3 billion light-years of space before striking Earth. The energy released in that fraction of a second exceeded what our sun produces in 10,000 years. Lorimer spent months checking and rechecking. Could it be interference? A satellite? A microwave oven in the observatory cafeteria? Every mundane explanation failed. The signal's dispersion, the way different radio frequencies arrived at slightly different times, proved it had traveled through intergalactic space, scattering off free electrons across cosmic distances. He published his findings in 2007. Astronomers called it the Lorimer burst, and many dismissed it as an anomaly, an interesting fluke, a cosmic one-off. But in 2013, something changed everything. The Arecibo Observatory in Puerto Rico, one of the most sensitive radio telescopes ever built, detected 4 more bursts, then 6 more, then 11. Each one displayed the same impossible characteristics: millisecond duration, enormous energy, and sources billions of light years away. These weren't anomalies, they were a phenomenon. Scientists designated them fast radio bursts, FRBs, and began the largest coordinated search in radio astronomy history. Within 5 years, they detected over 100. Today, that number exceeds 1,000 confirmed events, and our instruments catch only a tiny fraction of what's out there. Statistical analysis suggests that approximately 10,000 fast radio bursts strike Earth every single day. Think about that. Right now, as you process these words, invisible signals containing unimaginable energy are washing over this planet from sources so distant their light left before Earth existed. Most pass undetected through our bodies, our buildings, our atmosphere, phantoms from the edge of observable space. The first mystery, the energy. Imagine compressing all the sunlight that falls on Earth over an entire day. Every photon that illuminates continents, warms oceans, drives photosynthesis in every plant, and releasing it in a single millisecond burst. That's the typical power of a fast radio burst. The second mystery, the distance. These signals originate from other galaxies, not nearby stars or even distant regions of the Milky Way, but external galaxies, billions of light years away. The most distant FRB detected so far, designated FRB 2022-0610A, traveled for 8 billion years before reaching Earth. When that signal began its journey, our solar system hadn't yet formed. The third mystery, the frequency. FRBs emit primarily in radio wavelengths, around 1.4 gigahertz, the same frequency hydrogen atoms naturally emit in space. This is the most fundamental spectral line in the universe, the cosmic background hum of the most abundant element in existence. It's also the frequency that intelligent civilizations would logically monitor, what SETI researchers call the cosmic water hole. Coincidence? Perhaps, but coincidences accumulate. When scientists first detected FRBs, the leading theory seemed obvious: collisions between neutron stars. These ultra-dense stellar corpses contain more mass than our sun, compressed into spheres just 20 kilometers across. When they collide, they should release exactly the kind of catastrophic energy we observe. Except for one problem. Some fast radio bursts repeat. In 2016, astronomers identified FRB 121102, a source that produces multiple bursts over time, not just 2 or 3, but hundreds of detections from the same location in space. A neutron star collision is a one-time event. It destroys both objects completely. You can't have the same collision happen twice, let alone hundreds of times. The non-repeating FRBs could still be collisions, but the repeating ones require a different explanation entirely. They suggest something more persistent, something that can generate these enormous energies repeatedly without destroying itself. Something that might even be producing them deliberately. Here's what made scientists uncomfortable: the patterns. FRB 121102 doesn't burst randomly. Its emissions follow a 157-day cycle, active for 90 days, silent for 67 days, then active again. That's not the behavior of random cosmic catastrophes. That's the behavior of something with a rhythm, a schedule. Another repeating source, FRB 180916, displays a 16-day cycle with such precision that astronomers can predict when it will burst within hours. Imagine a cosmic lighthouse pulsing on a predetermined schedule across billions of light years. But the evidence forces us to confront an uncomfortable possibility. What if these aren't accidents? What if they're not the random byproducts of violent stellar death? What if something is creating them? To answer that question, we need to understand exactly what we're detecting. And when scientists examined the details, the specific characteristics hidden in the radio waves themselves, they found signatures that shouldn't exist.
Scientists discovered the first crucial clue buried in the structure of the radio waves themselves. When electromagnetic radiation travels through space, it encounters free electrons, charged particles floating in the near vacuum between galaxies. These electrons slow down lower frequency radio waves slightly more than higher frequency waves, creating a measurable delay called dispersion. By measuring this dispersion, astronomers can calculate exactly how far the signal traveled. It's like reading cosmic breadcrumbs. And when they calculated the dispersion measures for fast radio bursts, they found something remarkable. The signals had traveled through precisely the amount of matter predicted by our models of the universe's structure. This confirmed they weren't local phenomena. They were genuinely extragalactic, messages from the deep cosmos. But here's where it gets strange. The amount of dispersion varied in ways that mapped cosmic structure. In 2020, astronomers traced multiple FRBs to specific host galaxies and found they originated in galactic regions undergoing intense star formation, vast stellar nurseries where massive stars are born and die rapidly. These are chaotic environments filled with supernova explosions, stellar winds, and collapsing gas clouds. Yet the bursts emerged from these regions with extraordinary precision. Their radio frequencies showed bandwidth narrower than what natural astrophysical processes typically produce. It's like hearing a pure musical note emerging from a thunderstorm. Technically possible, but statistically improbable. Dr. Shami Chatterjee at Cornell University analyzed the characteristics of FRB 121102 and found the emissions were linearly polarized, meaning the radio waves oscillated in a single plane rather than randomly. This suggests they passed through or were generated by extremely powerful magnetic fields, on the order of 1,000 trillion times stronger than Earth's magnetic field. Only one type of object we know possesses such fields: magnetars. Magnetars are neutron stars with magnetic fields so intense they warp the quantum vacuum of space itself. These stellar remnants spin at tremendous speeds, some completing rotations in fractions of a second, while generating magnetic fields that would kill a human from 1,000 kilometers away by disrupting the electrical impulses in their nervous system. In April 2020, astronomers finally caught one in the act. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, detected a fast radio burst from within our own galaxy, just 30,000 light-years away. Designated FRB 200428, it originated from SGR 1935+2154, a known magnetar in the constellation Vulpecula. Finally, a source, a confirmation. magnetars can produce fast radio bursts. But this discovery solved one mystery only to deepen another. Because FRB 200428 was weak, 10,000 times less energetic than the typical extragalactic fast radio burst. If magnetars produce FRBs, why are the local ones so much weaker than the distant ones? Either we're observing two completely different phenomena that happen to look similar, or the distant FRBs require something far more powerful than ordinary magnetars. Some researchers proposed hyperflares, catastrophic releases of magnetic energy when a magnetar's crust fractures. These events might release enough energy to match extragalactic observations. But hyperflares are exceedingly rare, observed only a handful of times in decades of observation. They can't explain thousands of daily FRB detections. Dr. Bing Zhang at the University of Nevada proposed a different model. Magnetars aren't the source itself, but rather the lens. Perhaps something else produces the raw energy, and magnetars focus and amplify it through their extreme magnetic fields like cosmic amplifiers. But amplifying what? That question leads us deeper into speculation. The most remarkable discovery came from examining the fine structure within individual bursts. Modern radio telescopes can resolve fast radio bursts with microsecond precision. At this scale, scientists discovered something extraordinary. Many FRBs contain multiple subbursts, discrete peaks of emission separated by milliseconds or microseconds following specific patterns. FRB 121102 produces bursts containing up to 40 individual subbursts. Some arrive in descending frequency, a pattern called a sad trombone, where each successive pulse drops slightly in pitch. Others show complex modulation patterns where the intensity rises and falls in ways that resemble, well, modulation. Dr. Michael Hipke, an independent researcher in Germany, analyzed these patterns and found some contained periodic structures that repeated every 187.5 milliseconds. A pattern so precise it initially triggered speculation about artificial origins. Let me be clear, the overwhelming scientific consensus attributes these patterns to natural astrophysical processes. Rotating neutron stars, plasma instabilities, or propagation effects. But the patterns exist, they're real, and they're unexplained. But this represents just one piece of a much larger puzzle. Because in 2022, astronomers made a discovery that changed everything about how we understand fast radio bursts. They found one that shouldn't exist according to any theory, a burst that broke the rules.
To understand why this discovery matters, we need to examine not just what arrives at Earth, but what these signals reveal about conditions at their source. Physics operating under extremes we cannot replicate. Conditions that push matter and energy to their absolute limits. On October 9th, 2022, gamma-ray observatories detected the most energetic explosion observed since the Big Bang. Designated GRB 221009A, this gamma-ray burst released energy equivalent to converting 8 entire suns into pure radiation in less than 10 seconds. The explosion occurred 2.4 billion light-years away, yet it was so powerful that its radiation measurably ionized Earth's upper atmosphere. The first time any extragalactic event had directly affected our planet. Hidden within this gamma-ray burst, CHIME detected something extraordinary. A fast radio burst, synchronized perfectly with the gamma-ray emission. This was the first confirmed association between an FRB and another high-energy astrophysical phenomenon. And it suggested something profound. Fast radio bursts might not be isolated events, but rather one signature among several produced by whatever catastrophic process generates these energies. But what process? What mechanism can produce simultaneous gamma rays and radio waves with such staggering power? Dr. Wenbin Liu at Princeton University proposed that the answer lies in shock waves. When a massive star collapses into a black hole, it sometimes produces jets, streams of matter and energy ejected at nearly the speed of light from the poles. These jets punch through the collapsing star's outer layers, creating shock waves that accelerate particles to incredible energies. If these shock waves interact with dense material, perhaps remnants of the progenitor star's outer layers, they could generate both gamma rays and radio bursts simultaneously. The gamma rays come from the shock itself, while the radio emission comes from the trailing edge where the shock energizes plasma. This model explains the GRB-FRB connection, but it doesn't explain the repeating fast radio bursts, which clearly can't result from one-time stellar collapses. Which brings us back to magnetars, and to an even stranger possibility. In 2023, astronomers using the 500-meter aperture spherical telescope, FAST, in China, detected something unprecedented from FRB 2019-0520b, one of the most actively repeating sources known. Over 1,863 bursts in 47 days. That's an average of 40 bursts per day from a single source. No stellar explosion or catastrophic collision could sustain such activity. This source was doing something continuously, repeatedly, reliably. But the most remarkable finding involved the environment around this source. FRB 2019-0520b showed an unusually large rotation measure, a property indicating the radio waves had traveled through extremely dense plasma. The only explanation: this source sits embedded within a dense nebula, perhaps the remnant of the supernova that created the magnetar. Dr. D. Lee, chief scientist at FAST, suggested that these young magnetars, perhaps only decades or centuries old, sit in persistent environments that continuously feed them material, allowing them to produce repeated bursts as they consume surrounding matter. But consume it how? And why do the bursts follow such precise patterns? The answer might involve some of the most extreme physics in the universe: quantum mechanics operating at cosmic scales. Magnetars don't just have strong magnetic fields, they have fields so powerful they enter the quantum critical regime, where the field strength itself alters the quantum vacuum. At this level, virtual particle-antiparticle pairs spontaneously emerge from empty space, affected by the magnetic field's geometry. Dr. Christopher Thompson at the Canadian Institute for Theoretical Astrophysics proposed that magnetar bursts result from quantum mechanical instabilities in the neutron star's crust. As the magnetic field evolves, it stresses the crust until fractures occur, releasing enormous magnetic energy in sudden discharges, like cosmic lightning bolts, but powered by quantum mechanics. If true, we're detecting not just distant explosions, but quantum mechanical processes operating at scales billions of times larger than typical quantum phenomena. Fast radio bursts might be the universe's way of amplifying quantum effects to cosmic proportions. But here's what troubles theoretical physicists. The energies still don't add up. Even the most optimistic models of magnetar flares fall short of explaining the most powerful fast radio bursts by factors of 10 to 100. The brightest FRBs release energies that would require converting a significant fraction of a magnetar's rotational energy in milliseconds, a process that should tear the neutron star apart. Yet the repeating sources continue producing bursts for years without apparent degradation. Some researchers have proposed more exotic solutions: binary magnetar systems where two ultra-dense objects orbit each other, their interacting magnetic fields producing the bursts, or magnetars accreting matter from companion stars, using infalling material to power continued emissions. But others have suggested something far stranger: that we're not observing explosions at all. What if fast radio bursts are beams, directed transmissions from rotating sources that sweep across space like lighthouse beacons? In this model, we only detect bursts when the beam happens to point toward Earth. Most of the time, these sources emit continuously, but the beams point elsewhere, invisible to our telescopes. This would explain the precision, the patterns, the repeating cycles. It would also mean there are far, far more of these sources than we realize. Thousands or millions of beaming objects across the universe, and we detect only the fraction whose beams happen to intersect our tiny planet. The evidence extends beyond individual bursts into the realm of cosmology itself. Because fast radio bursts, with their measurable dispersion, offer a unique tool. They allow us to map the universe's structure. Each burst carries a record of every particle it encountered during its billion-year journey, creating a kind of cosmic X-ray, showing the distribution of matter between galaxies. Using FRBs, astronomers have confirmed that approximately half of the universe's ordinary matter, the protons, neutrons, and electrons that make up planets and stars, resides in intergalactic space as diffuse plasma. This missing baryon problem has puzzled cosmologists for decades, and fast radio bursts provided the first direct evidence. But they've also revealed something unexpected. The universe's matter isn't evenly distributed. FRBs trace enormous structures, vast filaments connecting galaxy clusters, regions where dark matter's gravity has drawn ordinary matter into cosmic webs. And some of these structures show patterns we don't fully understand. Which brings us to the most profound question. If we now know where fast radio bursts come from and roughly how they're produced, why do they exhibit characteristics that seem almost purposeful? Why do they follow patterns? Why do they repeat on schedules? To answer that, we need to examine not just the physics, but the implications.
Dr. Avi Loeb, chair of Harvard's astronomy department, posed a provocative question in 2017. Could fast radio bursts be artificial? Not likely, he emphasized, but scientifically possible. And possibility demands investigation. Loeb calculated that a sufficiently advanced civilization could generate fast radio burst energies by collecting sunlight across an area twice Earth's diameter and focusing it into a radio beam. The purpose? Powering interstellar spacecraft using photon pressure from the beam. In this scenario, we're detecting the spillover from extraterrestrial propulsion systems, the cosmic equivalent of seeing reflected sunlight from satellites. The repeating patterns, regular launch schedules, the varying intensities, ships at different distances, the precise frequencies, optimal transmission bands for maximum efficiency. Most astronomers find this hypothesis unnecessary, given natural explanations, but Loeb's point stands. Nothing in physics forbids such technology. If one civilization could develop it, others might follow. And in a universe containing perhaps 200 billion trillion stars, even unlikely scenarios become statistical certainties somewhere. The question isn't whether such civilizations exist. The Drake equations suggest they might. The question is whether fast radio bursts represent their signatures. This forces us to reconsider fundamental assumptions about detection. The search for extraterrestrial intelligence has traditionally focused on narrow-band signals, pure tones like those from radio stations, assumed to be obviously artificial. But an advanced civilization might deliberately use broadband bursts that mimic natural phenomena, embedding messages in patterns that require sophisticated analysis to recognize. Dr. Michael Hipke examined FRB 121102's subpulse patterns using various mathematical transforms, techniques that reveal hidden periodicities. He found some patterns that, while explainable by plasma physics,
also matched what communication theorists call chirped signals, broadcasts that sweep through frequencies to maximize transmission through dispersive media. This doesn't prove artificiality. Many natural processes produce chirped signals, but it demonstrates that distinguishing natural from artificial might require more than just looking for obvious beacons. The breakthrough would come from detecting modulation, information encoded in amplitude or frequency variations. So far, no confirmed information content has been found in any FRB, but we've analyzed only a fraction of the data. Competing interpretations divide the astronomical community into roughly 3 camps. The catastrophic camp argues FRBs result from one-time cataclysmic events, like neutron star mergers, collapsing massive stars, or interactions between compact objects and black holes. These explain non-repeating bursts well, but struggle with repeaters. The magnetic camp attributes most or all FRBs to various magnetic processes, flares, earthquakes, or interactions with surrounding material. This explains repeaters, but struggles with the energy problem and diversity of observed characteristics. The exotic camp proposes more speculative mechanisms, collapsing dark matter halos, evaporating primordial black holes, cosmic strings snapping under tension, or even phase transitions in vacuum states from the early universe. None of these frameworks explains everything. The truth likely involves multiple mechanisms, different types of FRBs from different sources, all producing similar observational signatures that challenge our instrument's resolution. Dr. Emily Petroff at the University of Amsterdam, who discovered some of the first repeating FRBs, suggests we're in the butterfly collection phase, gathering specimens and categorizing them, but not yet understanding the underlying biology. We have the observations, we're working toward the theory.
What leading physicists agree on, fast radio bursts represent extreme physics laboratories. At FRB sources, matter exists in states we cannot recreate experimentally. Densities exceed atomic nuclei, magnetic fields reach quantum critical strengths, energies approach the Swinger limit, where electromagnetic fields spontaneously create matter-antimatter pairs from vacuum. These are natural particle accelerators far exceeding anything humans can build. The Large Hadron Collider at CERN reaches energies of 13 trillion electron volts. Fast radio burst sources operate at regimes of 10 to the 20 electron volts or higher, energies where quantum mechanics, general relativity, and particle physics merge into a unified but poorly understood framework. By studying FRBs, we probe physics at these extremes. We test predictions of quantum field theory in curved spacetime. We observe how matter behaves at temperatures and densities present only in the first microseconds after the Big Bang. They're not just astronomical curiosities, they're cosmic laboratories. And the experiments are accelerating because new instruments coming online will transform our ability to detect, locate, and analyze these signals, potentially answering questions we've barely begun to formulate. Recent breakthroughs suggest we're on the verge of a revolution in fast radio burst science. The Square Kilometre Array, currently under construction across Australia and South Africa, will be 50 times more sensitive than any existing radio telescope. When it becomes operational in 2028, scientists estimate it will detect fast radio bursts at rates exceeding thousands per day. This quantity transforms quality. With enough detections, we can perform statistical analyses currently impossible. We'll identify rare subclasses, test theoretical models against vast datasets, and potentially detect the weakest, most distant bursts from the universe's first galaxies. Dr. Ryan Shannon at Swinburne University in Australia predicts the SKA will detect FRBs from galaxies so distant their light left less than 2 billion years after the Big Bang. These bursts traveled through nearly the entire history of the universe, carrying information about cosmic evolution, the formation of first stars, and the distribution of matter when the universe was young and strange. But detection represents only the first step. The real breakthrough will come from localization, pinpointing exactly where each burst originates. Current instruments localize FRBs to regions sometimes thousands of light years across. The Hubble Space Telescope can then image the host galaxy, but identifying the precise source within that galaxy remains challenging. The next generation of interferometric arrays, networks of radio telescopes working in coordination, will achieve arc-minute or even arc-second precision. This means identifying not just the host galaxy, but the specific stellar neighborhood, potentially even the individual star system. What scientists might find shocks the imagination. Perhaps supermassive black holes at galaxy centers, using their immense gravitational and magnetic fields to accelerate matter and generate bursts. Perhaps exotic compact objects predicted by theory but never observed. Quark stars, boson stars, or other strange matter configurations. Or perhaps something entirely unexpected.
The implications extend beyond astrophysics into fundamental physics. Fast radio bursts offer unique opportunities to test Einstein's general relativity at cosmic scales. According to relativity, different types of radiation should travel at identical speeds through vacuum. Light, radio waves, gamma rays, all moving at exactly the speed of light. But some quantum gravity theories predict tiny violations, differences of perhaps 1 part in a quadrillion, where higher energy photons travel infinitesimally slower than lower energy ones. Over billions of light years, these minuscule differences accumulate into measurable delays. When astronomers detected the FRB associated with GRB 2210-09A, they timed the arrivals of radio and gamma ray photons with nanosecond precision. Both arrived simultaneously within measurement error, confirming Einstein's prediction to unprecedented accuracy and ruling out entire classes of quantum gravity models. Future detections will push these tests further, potentially revealing physics beyond the standard model, subtle quantum effects of space-time itself. Perhaps the most profound implication involves the search for intelligence. If even a small fraction of fast radio bursts prove artificial, it would represent the most significant discovery in human history, proof we're not alone. But verification requires extraordinary evidence. The Breakthrough Listen initiative, funded by tech billionaire Yuri Milner, now dedicates telescope time specifically to FRB follow-up observations. When a burst is detected, automated systems immediately point sensitive instruments at the source, searching for follow-up signals, modulation patterns, or anomalies inconsistent with natural sources. So far, nothing definitive. But the search has just begun. Dr. Steve Croft at the Berkeley SETI Research Center emphasizes that absence of evidence isn't evidence of absence. We've analyzed perhaps 1% of detectable FRB characteristics with perhaps 1% of necessary sensitivity. The parameter space, the range of possible signal types, remains largely unexplored. And there's a darker possibility some scientists reluctantly acknowledge. Perhaps we're detecting artificial signals, but lack the framework to recognize them. In advanced civilizations, communications might look nothing like our radio broadcasts, might be optimized for efficiency, compressed, encrypted, or modulated in ways our pattern recognition algorithms don't detect. We might be surrounded by conversation and hear only noise. This brings us to the most profound questions fast radio bursts raise about the nature of reality itself. Because these signals, traveling for billions of years across expanding space, carry something beyond information. They carry time. When we detect a fast radio burst from 8 billion light years away, we're not seeing that galaxy as it is, we're seeing it as it was when the universe was younger, denser, and stranger. We're receiving a photograph from the past, a fossil message from cosmic epochs long vanished. Some of those source galaxies no longer exist in recognizable form. They've merged with other galaxies, been consumed by larger structures, evolved beyond recognition. The stars that created the magnetars that produced the bursts have long since exhausted their fuel and collapsed. Yet the messages persist, propagating through space at light's finite speed, carrying evidence of events whose physical causes have ceased to exist. They're ghosts. Electromagnetic phantoms haunting the cosmos, bearing witness to a universe that was.
And when they finally arrive at Earth, striking our telescopes with enough energy to ionize atoms, they create the only evidence those distant sources ever existed. A millisecond flash in the data, a spike on a graph, a pattern in the noise. Ephemeral, eternal, both simultaneously. Which brings us to the edge of understanding, to the questions that cannot yet be answered, the mysteries that deepen even as evidence accumulates, the implications that stretch beyond science into philosophy. The most mind-bending implications emerge when we consider what fast radio bursts reveal about the nature of causation itself. Here's the problem. Some FRBs we detect left their sources when Earth was still a molten ball of rock, before life existed, before photosynthesis, before the first cell divided. Those signals traveled through billions of years of cosmic expansion, threading through evolving galaxy clusters and void structures, finally arriving now, precisely when we've developed the technology to detect them. From the signal's perspective, no time passes. Photons don't experience time. Relativity tells us that at light speed, departure and arrival occurs simultaneously. The universe's entire history collapses into a single eternal moment from the signal's reference frame. But from our perspective, billions of years separate cause and effect. The burst's creation and our detection are separate events connected by a thread of electromagnetic radiation stretching across half the observable universe. Which raises a profound question. Does the universe somehow know we're here to detect these signals? Is our observation necessary to collapse the quantum wave function of distant events into definite states?
This isn't mysticism. It's quantum mechanics applied to cosmic scales. The famous double-slit experiment demonstrates that particles behave differently when observed. Extend this to cosmological scales, and some interpretations of quantum mechanics suggest the act of observation itself shapes reality. Physicist John Wheeler proposed a thought experiment called the delayed choice scenario. Imagine light from a distant quasar bent by a gravitational lens into multiple paths. If we measure which path the photon took, it behaves as a particle. If we don't measure, it behaves as a wave, taking both paths simultaneously. But here's the twist. The photon began its journey billions of years ago. Our choice of measurement today, particle or wave, seems to retroactively determine which path it took in the distant past. Fast radio bursts present a cosmic version of this paradox. The bursts travel for billions of years as coherent electromagnetic waves. Only when they strike our detectors do they collapse into definite events, measured, recorded, analyzed. Without detectors, without observers, do the bursts exist as definite events, or do they remain in quantum superposition, both detected and undetected, both particle and wave, until consciousness collapses them into definite states? Another unsolved mystery involves the apparent fine-tuning of fast radio burst properties for detection. FRBs emit primarily at frequencies that penetrate Earth's ionosphere with minimal distortion. They arrive with intensities just strong enough to exceed background noise, but not so strong they saturate detectors. Their dispersion measures fall in ranges that allow precise distance calculations. Coincidence or selection bias? We only detect bursts with these properties, while countless others go unnoticed. Dr. Matthew Bales at Swinburne University suggests we're observing the tip of the iceberg, the brightest, most easily detectable fraction of a vast population of fainter, more numerous sources. Our current instruments create a detection window, and we see only what fits through that window. Future, more sensitive instruments should detect these fainter sources. If they don't, if FRBs have a minimum brightness with few or no fainter examples, it would suggest something deeply strange about their production mechanism. It would imply a preferred energy scale, a natural tendency for the universe to produce emissions at precisely the level we happen to detect. Some physicists find this troubling. It feels anthropocentric, too convenient, too perfectly scaled to our observational capabilities, yet the data might demand such conclusions. The most disturbing implications involve what fast radio bursts might eventually reveal about the universe's large-scale structure. Because these signals, traveling across cosmic time, map not just where matter was, but where dark energy operates.
Their arrival times contain information about the universe's expansion rate, the distribution of invisible matter, the evolution of cosmic voids. Some theoretical models predict that anomalies in expansion, local variations in dark energy density, should subtly affect FRB arrival times. If we detect such anomalies, it would suggest the universe isn't uniformly expanding. Instead, it's patchy, inhomogeneous, with regions accelerating differently. This would shatter our cosmological models. It would require new physics, and it might explain persistent tensions in measurements of the universe's expansion rate, the so-called Hubble tension, where different measurement methods yield incompatible results. Fast radio bursts might be the key to resolving this crisis, or they might reveal it's worse than we thought, that our fundamental understanding of cosmic expansion, dark energy, and the universe's ultimate fate requires complete revision. And finally, the possibility that troubles everyone but cannot be dismissed. What if some fast radio bursts are signals? Not from magnetars, not from collisions, but from something else. Something that intentionally generates these patterns, transmits these energies, sends these messages across cosmic distances. The scientific method demands we consider all hypotheses consistent with evidence, and nothing in physics forbids artificial FRBs. The energies required are enormous, but not impossible for sufficiently advanced civilizations. The patterns observed, while explainable naturally, remain unexplained in detail. If even one fast radio burst proves artificial, the implications cascade. We're not alone. Intelligence exists beyond Earth, and it operates at scales and energy levels far beyond our current capabilities. But here's the truly unsettling thought. Perhaps we've already received messages. Perhaps the patterns are there, encoded in subpulse timing, frequency modulation, polarization states, and we simply lack the conceptual framework to recognize them. We might be like primitive humans hearing radio static, aware something exists but unable to decode the content. The universe might be speaking, and we hear only noise, mistaking messages for mechanics, communication for cosmic catastrophe. Until we develop the right analytical tools,
The right theoretical frameworks, the right questions to ask, we might never know the difference. We've journeyed through evidence spanning billions of years and light years, from that first millisecond burst detected in archived Australian data to thousands of daily detections across the globe. From simple radio signatures to complex subpulse structures suggesting impossible energies and unexplained patterns. We've learned that magnetars, the most magnetic objects in the universe, can produce fast radio bursts through quantum mechanical processes operating at cosmic scales. That these bursts carry records of the universe's structure, mapping invisible matter and probing dark energy. That they test fundamental physics at extremes we cannot replicate. And we've confronted uncomfortable possibilities, that these patterns might be more than random, that intelligence might operate at scales we haven't imagined, that the universe might be far stranger, far more populated, far more alive with communication than our instruments can yet reveal. The current scientific consensus holds that fast radio bursts result from natural astrophysical processes, primarily magnetar activity, possibly supplemented by other extreme events. No confirmed artificial signals, no evidence of intelligence. Just physics at its most extreme, matter in its most exotic states, energy at its most concentrated. But consensus isn't certainty. It's our best understanding with present evidence. And the evidence keeps accumulating, revealing new complexities, new patterns, new mysteries. Every answer generates new questions. Every solution exposes new problems. And standing at the boundary of knowledge, looking out toward the dark, we realize how much remains unknown. Thousands of signals strike Earth every day from sources billions of light years away, carrying energies that dwarf solar output, following patterns we don't fully understand, revealing a universe more extreme, more dynamic, more mysterious than we imagined. They're still arriving, right now. Invisible radio ghosts from galactic distances, passing through your body, through the air, through the ground. Phantoms from the edge of reality, carrying messages we've only begun to decode. And somewhere in distant galaxies whose light left before Earth existed, the sources continue their work, whatever that work might be. Magnetars convulsing in death throes,
neutron stars fracturing under impossible stresses, or perhaps something else, something stranger, something we haven't yet imagined. The signals travel outward at light speed, expanding spheres of electromagnetic radiation, carrying information about events long finished, propagating through the expanding cosmos, waiting for receivers that may not yet exist. Some will reach Earth in millions of years. Others will miss us entirely, passing through the empty space where our planet orbited before continuing into the cosmic dark. Messages without recipients, information without audience, broadcasts into the void. The universe is vast, its mysteries endless, but across the incomprehensible distances, through billions of years of darkness, signals arrive, phantoms from the edge of reality, whispering secrets about the cosmos's most extreme phenomena. And we've only just learned to listen. The phantom signals continue. The search goes on.